Besides electric fields, we can also use magnetic fields to exert a force on moving electrons. And so recall that this goes via the Lorentz force, for which we have the force being equal to the charge of the electron minus E times the cross product of the velocity of the electron v with the applied magnetic field. And so on first sight, just like with the electric field, this gives us a problem because in a homogeneous magnetic field, this would just give us a deflecting force, a force directed in one direction. So also here we play a special trick for applying a non-homogeneous magnetic field. So actually magnetic lenses are often encountered in electron microscopes, more often than electrostatic lenses. So here you see a photo of a cut through of a transmission electron beam column, where you can see the copper wires of the coils surrounding magnetic material that brings a magnetic field to the optical axis. So here you see a zoom in, where you can clearly see the individual wires in the copper, and you can actually see that in this case the sample holder is in between two lenses. So let's first draw the situation as we have seen in this image.
Recording and action.
So here we have the two magnetic bores of the lens, and the optical axis is arranged here. So what you just saw in the picture is that in this case, this area here, we have our copper windings that magnetizes all this magnetic material. So in this position the same. So here we have our copper wires around the magnetic material, and then all this material gets magnetized so that in the end we have a magnetic field in between these two pole shoes here. So in this case, say the magnetic field points in a downward direction. So just like with our electrostatic field, here also the fact that we have an opening creates a bending of magnetic field lines. In this case here, going like this. Yeah, so all this is our magnetic field B. And now we can already see that if we have an electron pass through here, if the electron goes on axis, so this is the velocity of the electron beam, the velocity direction, so these are our electrons. If it goes on axis, the magnetic field is oriented in the same direction as the velocity, which gives us a 0 for the force that is being exerted. Now, of course, the interesting thing is what happens if we move slightly off axis. So I'm going to draw that situation here. Say we have our axis here. So the dashed line is our optical axis. And now I'm going to put my electron next to the optical axis. So say we have our electron here. Yeah, this is our electron. It's traveling along the optical axis when it enters the magnetic field region. So here it's traveling, but now slightly on this side of the optical axis. And that means that the magnetic field in this case is pointing under an angle towards the optical axis. Yeah, so we have our magnetic field in this direction. Now we can find the direction of the Lorentz force by applying the cross product. So that for that we have to use our right hand, turn the magnetic field vector turn the velocity vector to the magnetic field vector, and if we do so, our thumb of our right hand points in the direction of the Lorentz force. If we do that, we'll see that that one points towards us. However, the electron is negatively charged, so meaning the direction of the force will contain a minus sign. So in this case, the Lorentz force will be pointed into a screen. And so this does not give us a focusing force. This means the electron will start moving in a plane perpendicular to its travel direction. So let's see what that means for the movement. So for that, we're now going to draw the new situation after the electron has entered the electric field. And I'm going to draw the projection along this plane, so a plane perpendicular to the optical axis. Yeah, so I'm going to draw that here. So now we have the optical axis here. Yeah, so the optical axis now goes through our screen. This is in yellow. It's again the optical axis. So we now have our electron traveling here. And so we look at it from the top. We see the axis, we see the electron. It's traveling along the optical axis, but due to the Lorentz force here, it also has gained a velocity perpendicular to the plane, perpendicular to the axis. So in this case, that velocity is in this direction. And so I will denote this with v perpendicular, so it's the component of the velocity in the perpendicular direction. Now our B field again points in the direction of the axis, so in this case the B field is pointing into our screen. And this again means that we get an additional direction for the Lorentz force. So the Lorentz force exerted by the perpendicular velocity. And again we can apply the right-hand rule, and we see now in this case the Lorentz force is pointed towards the axis. And similar to the case we've seen with electrostatic lenses, the further we go outside, the higher the curvature of the magnetic field, the stronger the component that we have pointing towards the axis here. So also in this case that will give us a stronger deflection field. So we see that the electron starts to move in the direction, starts to move in this plane, and then also starts to move towards the axis. If we would continue that trajectory, we will see that the electron will follow a circular motion, as is common for electrons or charged particles moving in a magnetic field. So what we have, if we would look at what happens with an electron traveling inside this field here, the electron would come into the field region. It will start its spiral motion, both in the plane and towards the axis. So I'm now going to draw that in a two-dimensional frame. It will move towards the axis, and then when it passes the center part of the lens, of course, the force will again be pointed outward. So in this case, the spiral motion will have the electron move out again. And then we see, in this case also, the net effect of the electron is a movement towards the optical axis and away from the optical axis. So a focusing of the electron beam towards the optical axis. Note also that typical for magnetic lenses is the spiraling circular motion that we see in this trajectory. So the fact that often magnetic lenses are used in electron microscopy and can also be immersing the sample means that we can never use magnetic materials inside an electron microscope. So also the sample holders should not be magnetized or of magnetizable material, because otherwise they will also feel the force exerted by the magnetic lenses and thus start to move inside our electron microscopy chamber. Also, of course, magnetic fields applied on the sample or by the sample will distort our focusing effect and thus deteriorate our imaging.